Hey, so this is Joe, and this is the second video of the 14th chapter of Stewart's Calculus, and we're going to be talking about partial derivatives. So partial derivatives can be expressed in these, or I should say first-order partial derivatives can be expressed in these two different kinds of notation. So this first kind is our f notation, so f sub x, or del f del x, at point AB, and we can write at point AB here, is the rate of change of a multivariable function in the x direction. And I'll show you what I mean by that on a graph a little bit later. And f sub y at AB and del f del y, these little things are dels, both at AB, is the amount the function is changing, or a multivariable function is changing at point AB with respect to y, or in the y direction, and so this is in the x direction. And we can write this out with our limit notation as the limit as h approaches 0 of the function a plus h b, so this is a function with two independent variables, so it's function in three dimensions, minus the function of a and b over h, and then with respect to y, the partial derivative in limit notation is the limit as h approaches 0 of f of a b plus h minus f of a b over h. So what this limit notation tells us is that in order algebraically to find the partial derivative with respect to x, what we have to do is we basically differentiate implicitly with respect to h, and we treat everything with a y as a constant. And when we take the partial derivative with respect to y, we basically leave everything with an x alone and treat those terms as constants, and then differentiate implicitly with respect to y. And I'll show you what I mean by that actually right now. We'll do one little sample problem. And then, and I'll show you how we can kind of think of these graphically. So, first we're going to do problem number 16 on page 936 in your book, and it asks us to find the partial derivative with respect to y and with respect to x of this surface, so this function in two variables. And on the previous screen I showed you how to find the derivative at a particular point, and really to find the partial derivative of a function like this generally, the general partial derivative, you just replace all those a's and b's with x's and y's. So we'd have del f del x, we'll find it first with respect to x. We'll find that to be the limit as h approaches 0 of f of x plus h y minus f of x y over h, and then an analogous thing for del f del y. However, we'll have the y plus h, and then this x plus h will just be an x. And so that means that to find this algebraically, we differentiate this implicitly, treating all the y's as constants. But before we do that, I want to kind of show you how we should be thinking of partial derivatives graphically. So let's go over and look at a graph of this function, and I'll show you what these partial derivatives mean graphically. Alright, so here we go. We have a function, or a graph of that function that we're dealing with. We've got the x-axis right here, and we've got the y-axis right here. And so when we talk about a partial derivative in the x direction, what we mean is basically the slope of the curve, or the surface I should say, at a particular point, wherever we're differentiating, going in either the x or y direction, depending on which partial derivative we're taking. So let's say we're trying to take the partial derivative of this function at this point. If we're taking del f del x, so the partial derivative with respect to x, what that will do is find the slope of this surface in parallel to the x-axis. So it would basically be the slope of this line right there. So it would be going up pretty steeply at this point right here. And that's del f del x. And del f del y would be finding the slope of the line tangent to the graph at that point, but parallel to the y-axis. So this line, that line that I just drew right there, that is going to be, that line is going to be del f, del y. And so the partial derivatives really kind of correspond to derivatives of the surface parallel to the x or parallel to the y-axis, depending on what the partial derivative is with respect to. And you can also think of this in terms of taking a cross-section of the function. If you could take a really small slice of this function in the x direction, so small that it actually ends up being a 2D graph, and you could look at it just as a curve, it would be the derivative at that point, and that's del f del x. And you could take, if you were able to take a little tiny cross section of this surface, I should say, parallel to the y-axis going through this point, and you were to think of that as a 2D graph, and then you take the derivative at this point, that's del f del y. So that's partial derivatives thought of graphically. Now we can algebraically solve this problem right over here on the next screen. So first we're going to find del f del x, and remember this question only asks us to find the general partial derivative with respect to x. So what we're going to have to do is we're doing it with respect to x, so the y we treat of as a constant. So we can think of that as that y to the y cubed is just an a. So what we do is we differentiate this x to the fourth normally. So we take a 4 out, we have our constant y cubed, we have our x, and then we lower this exponent by 1, and we make it x cubed. Plus, next term, so this y is a constant, and this 8 is a constant, so because we're differentiating x squared, we're differentiating with respect to x. We keep that 8y, and we bring down the 2, so that becomes a 16y, and that x squared becomes an x. So this is the partial derivative of f with respect to x. Now we'll find del f del y, and now we treat the x's as constants, and we differentiate all the y's normally. So this x to the fourth we treat it as like a constant, and this y cubed we differentiate normally. So we bring our 3 down, and we have our 3x to the fourth, and that y cubed becomes a y squared, plus, and then now the next term, this y is a constant, and we're differentiating this y, and this 8x squared is a constant. And when we have a constant times a variable to the first power, we just take the constant when we're taking the derivative. So that 8x cubed y just becomes an 8x, or not cubed, squared, just becomes an 8 squared. And so that is del f del y. And that's kind of basically how we go about taking partial derivatives. Alright, and so now we can talk about higher order partial derivatives. And higher order partial derivatives, there are a few more different kinds than the kinds of higher order single variable derivatives. And so here are two that should look pretty familiar. This is the second partial derivative with respect to x, and the second partial derivative with respect to y. And we can write these with our f notation and with our del notation. With our f notation, we have the xx, that means you take the partial derivative with respect to x of the function f, and then you take the partial derivative with respect to x of that already differentiated function, and both times is with respect to x, and you write it out like this. And this looks kind of analogous to our single variable partial derivatives, and since we only would be dealing with one variable, it would only be with respect to that variable twice, right? And with respect to y, it's the same deal. We have f sub y, and that is taking the second partial derivative with respect to y, so we take the partial derivative of f with respect to y, and then the partial derivative of that with respect to y again. However, because we're dealing with two variables in multivariable calculus, we can have multiple higher order derivatives than just this. We have these two partial derivatives, and these are kind of our mixed partial derivatives. And what they mean, so we have x, and what you might notice is in the subscript right here, the x and the y are in a different order than in the denominator here with the del notation. And so what these mean is, this one first, it means that if we have the partial derivative of f with respect to x, we take the partial derivative of that, but we take it with respect to y. So what we do to find this partial, and these partial derivatives, immediately I don't have a kind of physical explanation for you. With these, we can think of this one with respect to x, the second partial derivative with respect to x, we can think of that as the acceleration of a particle in the x direction, and this we can think of as the acceleration of a particle in the y direction. However, these two, we don't have that same sort of physical way of explaining it, but they become useful when we start using things like the Hessian, the Jacobian, and curls, and so forth. These become useful algebraically and explaining other physical phenomenon. But what it is, and how we take these kinds of higher order derivatives, because you will need to do so for this class, you take the partial derivative for this one. If you see the x in front in the subscript or the x second in the denominator, you take first the partial derivative with respect to x, and then you take the partial derivative of that differentiated function but with respect to y. And you do the opposite thing with this one. When you have the y in front, or the y is second in the denominator in the del notation, you take the partial derivative of f with respect to y, and then you take the partial derivative of that differentiated function, but you take it with respect to f. So those are all four higher order partial derivatives that you'll need to deal with when you have two independent variables. And when you have three independent variables, you get even more, but we're not going to really worry about that right now, and there are going to be very few instances, I feel like, in this course where you're going to need to deal with seriously taking higher order derivatives with three independent variables. But it's not too much more difficult than this. You'll just get a few with longer subscripts. But now we can talk about a theorem that relates these two higher order derivatives right here, and that is called Clairaut's theorem, and its French name spelled like that. And basically what it says, that if both of these higher order derivatives right here, so if f sub xy and f sub yx are continuous, so no holes, no jumps, or anything like that, then what we can say is f sub xy is actually equal to f sub yx. So actually, if both of these functions are higher order derivatives are continuous, then it doesn't actually matter in which order you do your partial differentiation. If you differentiate with respect to x or y first, because both of these higher order derivatives are going to be equal to one another. And so most of the time you can assume, for example, if f is a polynomial or f is like a single trig function, you can assume that these higher order derivatives are going to be continuous, and then based on Clairaut's theorem that they'll be equal. So now, that's kind of all you need for the basics of partial differentiation. And right now that we know about higher order partial derivatives, we're going to go back to that problem we were doing earlier and take the higher order derivatives for you. Alright, so these are the first order derivatives that we took earlier, and so now let's take all of the higher derivatives of this function. So first, we can start off with the second partial derivative with respect to x, and so that means we just take the derivative of this function with respect to x again. So we treat the y cubed as a constant once more, and so we're going to get a 12x squared y cubed plus, and then we treat this y as a constant, but since we've just got one x right there, that just becomes a 16y. Now we can do the same thing with respect to y. So that means you just take the derivative of this function with respect to y, treat that x to the fourth as a constant, and we'll get a 6y times x to the fourth plus, and then this whole thing is just a constant, so that's going to be a plus 0. Now we can take our higher order, our mixed higher order derivatives, and based on Clairaut's theorem, we can, if those two are continuous, then they're equal to one another. And right now, I will take both of them separately just to prove to you that when you have a polynomial like this, Clairaut's theorem will hold, and those two mixed higher order derivatives will be equal to one another. So first, let's take del f, del x, del y, which means that, so we took the derivative with respect to y first, so we deal with this function, and we take the derivative of this function, but with respect to x. So that means we treat this 3y squared as constant, and we bring that 4 down, and that'll become a 12 y squared x to the third plus, and now we take the derivative of this, that's going to be a 16x. And now we do the other mixed higher order derivative, but we have our y out in front and our x, so that means we deal with this function and we differentiate it with respect to y. So we bring that y down, we get a 12x cubed y squared, and here we'll just get a 16x because we treat this as constant and that y we're differentiating, but it goes away. So 16x. And you see these two are equal to one another, therefore Clairaut's theorem does hold, and we could have guessed that at the beginning, but these two are equal to one another. So that's pretty simple, straightforward partial differentiation using a polynomial. Now let's go do a slightly more complicated function. So we have a function u that is that has two independent variables, r and theta, and we are asked in this problem to find both of the first order partial derivatives of this function. So let's start off with del u del r. So that means that we're differentiating this function with respect to r implicitly. So we have an r inside the sine function. So that means we write that as cosine r cosine theta. First off, but we need to take the derivative of what's inside. This cosine theta we can treat of as a constant since we're differentiating with respect to r. So that r will go away, and this will just be a cosine theta. And that is because the chain rule still holds, remember, even with implicit differentiation. So that's del u del r. Now let's find del u del theta. And we've still got it, so we've still got a theta inside the argument of the sine function right here, so we need to differentiate that. So that'll be cosine r cosine theta. And we come inside and we need to take the derivative with respect to theta. Well, the theta is inside the cosine argument, so that means that this r, even though it being treated as a coefficient, still will pop up. But it'll still pop up. And so the derivative of cosine is negative sine, so we throw a little negative out there, and then we have our r sine theta, and those are the two first order partial derivatives. So that's it for kind of like the introduction to partial differentiation. Stay tuned for the rest of this chapter. We're going to get a little bit more involved. We're going to start finding some zeros and tangent planes and all that. So thanks for watching.